Alright, this is Chapter 2, Section 7. This is Part 2, the second half of the section. So, let's say we take the chip data from the previous section here we did, right? And we want to find 1.5 deviations above the mean and 3.25 deviations below the mean, right? What value would that be, essentially? So we'll go to our thing here. And we'll just merge those. We want 1.5 standard deviations above the mean, right? Okay, so we'll do the mean plus 1.5 deviations above, so that's plus, and the standard deviation is this, right? And then if we want, actually, it says, why did I do that there? I don't know. We'll put it in the middle. That kind of makes more sense. There we go. All right, so let's do, in this one here, we'll merge it, and we'll do 3.25 standard deviations below the mean. Okay, so you take the mean and you subtract 3.25 deviations below. Okay, so you get that number there. So that's the number of chips, correct? Chips and chips. Okay, so we go back to our document here. Okay, so what did we do? We did x bar plus 1.5 times the sample standard deviation, right? Because obviously it's not every, it's the S1 because it's not every single cookie in the whole world that we did. So that was 23.95 plus 1.5, and that was approximately 2.55 which we really don't know exactly. So it's that was approximately 27.77. Okay, 77728 keeps going, right? So format color blue, and we'll make this the answer. Oh, and do chips, right? A little space in there. Format color orange. Perfect. Okay, so that's the number of chips that represents 1.5 deviations above. So let's say we want to go below, right? All right, so we do minus for this one, right? Because we're going below. We're going 3.25 deviations. 3.25, so 3.25. And we got 15.65. So, okay, 6575. So 15.6575. Correct, double check. That is correct what we got. Okay, so pictorially, there's one of two things is going to happen. If it's approximately bell-shaped or normally distributed, right, which means, or non-skewed, then the empirical rule applies, right? So the empirical rule basically says that if you're 1 deviation, 2 deviations, 3 deviations above the mean, right? So that's, ooh, let me get rid of that extras here. Get rid of that. Boom. There we go. Okay, so 1 deviation, within 1 deviation is 1 above and 1 below, right? So that's approximately 68%, right? So it's approximately 68%. This is a little more close. It's like 34.13 ... It keeps going on if you split it halfway. So between 2 above and 2 below deviations, all of that data is approximately 95% of all the data values in the set. And 3 deviations, right, which is 3 above and 3 below, everything that falls in between is approximately 99.7% of the data. Again, it's approximate. When you do the calculus calculation, it doesn't quite work out that nicely, but you know, it's close enough. So whether you do different types of graphs, it still looks the same. So we do a histogram, same idea basically. Okay, so let's say we have an IQ data for its bell-shaped distribution, right? So we know it's normally distributed, right? So that means if I have 100 minus 2 times 15, right, is less than x, is less than, where x is IQ in this case, 100 plus 2 times 15. Right, well, why did I pick those values? Well, 100 minus 30 is 70 IQ. Right, and 100 plus 30 is 130 IQ, right? which is the value specified, format color blue, right? So between 70 and 130 is what percent of the score. So that's approximately 95% of IQs are between 70 and 130. Okay. So again, we're using the empirical rule. The empirical rule, right, is plus or minus 2 standard deviations, which is what we figured out, 70 and 130, right? And the empirical rule says 95% for 2 deviations, approximately. Might be a little more or less than that, but you don't know. Okay, assuming the data set is approximately normal. Oop, I left some space here. There we go. So normal, meaning we're using this up here. What's the percent that's greater than the mean? Well, if I'm greater than the mean, well, this is the mean right here, right? The middle is the mean. The greater is this half. Well, the whole thing's 100%, so obviously half of it's 50%, isn't it? So that's 50% of the data values, essentially. Okay, that's pretty easy to calculate. Greater than 1 standard deviation above the mean. Okay, so if I do greater than 1 standard deviation above the mean, well, this is 1 standard deviation above the mean here, right? So it's everything this way. The problem is this goes infinity this way, so you're better off just doing it the other way, which is minusing it from 1. So we'll do it from here, or from 50 rather. So 15.87. So essentially what I did was I took the latter half here, right? I took the latter half and I subtracted out this, which gave me what I want, which is all the values beyond there, essentially, because it goes forever in that direction, obviously, because there's no limit to whatever the thing is you're calculating or count. So less than 1 standard deviation above the mean. Okay, so less than 1 standard deviation above the mean. So if you think about what that means, okay, that's 1 deviation above the mean right there. We want less, so it's everything this way, correct? Okay. Did I get that right? Yeah. Wait a minute. So less than 1 standard deviation above the mean. Okay. So I gotta do a little math there. So I basically want to do the 50 plus the 15.87, right? So that's going to be 65.87, right? So basically, approximately, I can do either way. Approximately 65.87% of the data values. Okay, there we go. Okay, less than 1 standard deviation above the mean. Yep, 1 deviation above the mean. Yeah, there we go. Okay, so now we want between 1 standard deviation and then 2 standard deviations above the mean. Okay, so if again it's 1 below and 2 above. Okay, so let me just double check that here. 1 below and 2 above. Okay, so 1 below and 2 above would be all of this, right? So this middle 68 plus another 13.59. If you want to be more accurate, you can add those, right? So whether you do 68 or you add these, I don't care either way. It's close enough, because again, we're estimating. So who's to say who's more right at that point? And doesn't really matter all that much. Okay. All right, let's get this over here. That didn't work out correctly. Okay, I don't know why I did that, but anyways. That's the wrong letter, but whatever. So obviously the middle plus that one other piece there, so it's about 81.5% or whatever the case may be of the data values fall within there. Okay, but not everything is normal, right? As we know, they could be skewed, so it could be skewed left or right. So this is skewed right and this is skewed left, right? Skewed right, skewed left. different types of graphs. So in that case, you use Chebyshev theorem basically, which gives you a basement of a least value, which is based on k. All right, so k. Standard deviations, essentially. It's not bell-shaped, obviously, and it has to be greater than 1 because 1 minus 1 over 1 squared is 0, so it only works for greater than 1. You can do 1.5, 2, 3, whatever you want. You can do partial or less. You just use the formula, basically. So if you do 2 deviations, it's at least 75% of the data. 3 deviations is 88.9 at least, basically. And you can do 2.5 deviations, wherever you want. Just use the formula, essentially. Okay. So let's say the price of houses in a certain neighborhood are $50,000, a standard deviation of $10,000. So if I do plus or minus 10,000 to there with 2 deviations, that's really 20,000, right? So you add 20,000, you take away 20,000 from this, that's 30 to 70,000, correct? Okay. So the result is, when you do that, that is at least 75% of all the houses, right? Because does it say anywhere in here about being normally distributed? It does not. So you have to assume it's probably not normally distributed unless you can otherwise prove that. So at least 75% of the houses fall within this range, essentially. Okay, so let's say, excuse me, the men's heights are 69 inches. We've done this problem before. And the deviation is 2.8 inches, right? So we want to fall within 3 deviations. So 3 times 2.8, add it one way and subtract the other, right? Okay. So essentially, that's going to be between 60.6 and 77.4. So this is the range of 3 deviations, essentially, right? But again, we don't know if this is normal or not, so we're going to assume it's not normal. So I'm going to use Chebyshev's formula, right? 1 minus 1 over k squared, right? Which we're using 3 deviations. So that's going to give me 0.88 repeating. So 88.8% of men fall within this range, essentially, using Chebyshev's, right? We can't do an approximation with empirical because we don't know if it's normal or not. So we have to assume that it's not normal and use Chebyshev's, basically. Whether it's skewed left or right, we don't know. In reality, men's heights is actually skewed right, in reality, right? Mostly we're bunched up, and there's some guys that are really tall. You can't really short, really, because you wouldn't have any height at all, but there's not much of a limiting factor there. Okay. Alright, we did houses. Okay. So let's say the survey found the travel allowance of couriers is 25 cents per mile. The standard deviation is 2 cents. Determine the minimum percentage of data values that will fall between 20 cents and 30 cents. Okay, so we don't know if it's normal at all, right? So we want to do 30 cents minus 25 cents, right? It's because you can do the other way around too, because you can do 20 to 25 or 30 to 25. Either way, that's a deviation of 25 cents. That's more than the mean, right? So it's 5 cents more than the mean, right? So 30 cents is 5 cents more than the mean, and 20 cents is 5 cents less than the mean. Either way, it's deviating by 5 cents, correct? Okay, so that means K is equal to 5 cents. Crap, I messed that up. 5 cents over the 2 cents, right? That's the standard deviation, which is going to be 2.6 standard deviations, right? Okay. All right. So that's how many so 1 deviation is 2 cents. So 5 cents is 2.6 deviations, essentially. Okay. So 1 minus 1 over no, 2.5. What am I saying? I can't. 2.5. I don't know what I'm doing there. All right, I got to square that. Okay, so that's going to be 1 minus 1 over 6.25. Okay, which would be 1 minus 0.16, which is 0.84. So that means at least 84% of the data values. Okay, data values. Okay, at least 84% of the data values are going to fall within that range, basically, of the 20 cents to 30 cents, essentially, is what we're saying. Okay. Okay, so let's sum it up, basically. Okay, so I have a little problem down here. Alright, so this one is saying normal, this one is saying not normal, so this uses the empirical rule, this uses the Chebyshev rule, right? So if the data is approximately normal, then roughly what proportion of the data is between 27 and 57 miles per hour? Alright, if the average speed is 42 and the deviation is 15, essentially, right? Well, all I have to do is plus or minus, how many deviations did I say? Oh, okay, it'd just be 1, wouldn't it? Right? Because if you think about it, 42 minus 15, right? And then 42 plus 15 would be 57 and 20. 57 and 27, essentially, right? Which is approximately 68% of the data value. So how do I know that? Well, that's 1 deviation. So I go back to the rule here. If it's normal, right, 1 deviation is approximately 68%, because we're saying it's normal, right? It's not exactly 68, but close enough. Okay. Well, if it's not normal, okay, what about the same thing here? Well, there's the problem. We're still saying 1 deviation, aren't we? Right? Bump this over, bump this back. Okay, so if I put in 1 deviation here for Chebyshev, 1 minus 1 squared equals 1 minus 1, which is 0, so at least 0%. So again, if you remember the rule about Chebyshevs, right? Where do I have here? It has to be greater than 1, right? You can have 1.5 deviations, whatever the case may be, 1.2, 3.7, whatever the case may be. But you have to have more than 1 deviation for the Chebyshevs to work, essentially, for the minimum values that you would expect to fall within a particular range, essentially.